right, it's time, so let's get started. We have talked about logistic regression in the binary form, right, +1 and -1. Similar to linear classification, +1, -1. Over there, we say, well, there's a way to extend that to perform classification for more than 2 classes, yeah, by putting those perceptrons in a sequence. Not the best way to do things, but it can work. Turns out that to extend logistic regression to a multi-class, to more than 2 classes, it's a lot more convenient, yeah, than for the linear classification method. Okay, so it's a very natural form of extension because we consider probability now. So, what do we mean by multi-class logistic regression? Of course, that means we have the label y now is no longer simply +1, -1. No longer binary. We have, let's say, C classes of objects. You can say image identification is a dog, a cat, or a bird, right? Whatever you can imagine. So these are the labels. So you have to classify the given X vector into these C different classes. And you're given the training data set to do that, of course. Training data set will still be the same, right? X, Y, except that Y now can take C different values. Okay? So this extension is kind of obvious, right? So now, what is the hypothesis? Yeah? What is the hypothesis corresponding to the binary case for logistic regression? So what is the hypothesis? Or the hypothesis set. Because this is multiple classes, it turns out that we have to use multiple lines instead of a single line. Okay? So let's say we have C different lines. We collect them all in this big omega. Yeah, so we have omega 1, omega 2, and then omega C. Yeah, C different lines. And of course, we can also call them the weight vectors, right? We have weight vectors for the C classes. Yeah. And then we hypothesize. Now we have to logistic regression, right? So we have to hypothesize the probability of a X in this particular class, right? So we have to guess or hypothesize that the probability that the label yn is I, given the input xn, the attributes or the input vector, the data point xn, is the following: e raised to the power of wi transpose times xn. Okay? So you pick the i's wave vector. And then at the bottom, the normalizing term is simply the sum of all of this E of wi's. Yeah, but here the index is j, so wj xn like that. And this is, we hypothesize that this is true for all I. Yeah, for all classes, we have this structure. Okay, looks similar to what we have seen before, right? What we have seen before is e to the something, and the bottom is 1 plus e to the something. Yeah. So now we have so many classes, we say, okay, we just take this e to the something, sum them up all together so that we have a normalized form. Yeah? We need this normalization because these probabilities have to sum to 1, right? Because it's, the probability is that it is I, right? I is 1 to C. You know, all of these probabilities have to sum to 1, right? Yeah? So, and this function, as opposed to the sigmoid function that we have before, this is called a soft max function. Soft max. This is soft. Function. Yeah. And we denote this by, just like before, p hat of omega. Now because the variables are based in this big omega now, right? It's long vector. So just probability that, what is your estimation for that probability? Yeah, that the label should be I. Okay. So as you can see, this is a very natural extension to what we have seen before for the binary logistic regression. Yeah, still the same. Previously, we only have two kinds of probabilities. Now you have C different probabilities. Yeah, but they all should sum to 1. Okay. And then, of course, the error criterion would also be naturally extended. We're going to use the log loss error again. Right? En for the nth item, yeah, it is minus log of this probability that you estimate. Yeah. Whoops, sorry. Yn, xn, like that. Yeah. This is exactly the same as our binary case. Yeah. No change there. Right. Yeah. So therefore, the purpose for our optimization would be to find the best omega in to minimize the average of these ENs. Yeah, the E in will be defined similarly as before, or I should say exactly as before. Yeah, so you find the best omega to minimize this error. And now, just remember now that the omega contains C different W's. That's all. Yeah, C different lines that you have to optimize. So to do this, again, we have to use a numerical method to optimize this, and we go back to our good friend, the gradient descent. Yeah. So that means, well, we have to know how to find the gradient of this guy. Yeah. Turns out it's quite doable. It's not hard. Yeah. So, but one thing to know is that how does the gradient look? So this gradient with respect to this big omega now, right? Because this is a function of this big omega, all things. But by the definition of this gradient, remember what is the definition of gradient? Just the partial derivatives of all of the elements in this vector omega, right? So therefore, you can naturally divide this big vector into different components. Each one corresponds to one of the small omegas. Yeah. So this one, if you write it out as a one big vector, let's see. Yeah. So the gradient with respect to W1, yeah, En of big omega gradient. Remember, these are column vectors, right? Always, by default, these are always column vectors. So just put the columns one after the other. Now you have a long column vector, yeah? And then WC, En of omega, like that. Yeah? Everyone okay with this? Yeah? This just basic definition of the gradient, yeah? And so you see that this naturally we have C different vectors to calculate, C different gradients to calculate, yeah? And it turns out that you can calculate them separately. Yeah? Each can be computed separately, let's say, yeah? Each of these guys compute. Okay. Using our regular method, yeah? So once you have that, then you do a SGD update. Let's just write the SGD, yeah? But the GD, the full GD, will be, just a trivial modification, right? So for the iteration t, omega t will be equal to, of course, WT1, WTC. And then you just sample one of the data points. And uniformly around them, right? So just uniform. This is tilde means that you sample it from this distribution. Yeah, so uniform 1, 2, n of them. Yeah, pick one. And then for each one of these items, these W's, 1 to C, you compute the gradient, En, yeah, and then you update t plus 1 for I, is equal to t for I, yeah, minus this learning rate. Again, now it's just the gradient with respect to I is good enough. Yeah. So all of this update can be done separately. Yeah. I should say t here. This one, this big omega, there's a t there. T over here. And that's it. You know, you just keep updating until convergence. Yeah, and then you are all set with this. Okay. The only unresolved issue is how do I compute this gradient with respect to Wi, yeah, for this new form, for this softmax function. Looks like this, yeah. That one, how do you take the gradient of that one so that you can carry out the GD, okay? Turns out that taking the gradient of that one, there's a small twist there, yeah, it's not completely straightforward. So let's look into this. So how do we compute the gradient with respect to one of these lines, yeah, one of these wave vectors? So we compute this En, right? So n, that means we already chosen the nth sample point, right, at this stage. Yeah, you already chosen the nth example, and now you have to calculate the gradient with respect to this W. Did I say omega? No, W. Okay. It looks like omega. That's why people like to use a big omega to put them together. But yeah, W and omega. So this is given nth example. Turns out there are two different cases. Depending on whether this I, what it is. Yeah, this I, remember this I is the index to one of those classes, right? From 1 to C. Yeah. Turns out that it depends on whether this I that you have for this particular W matches the Ym, the true label. Yeah. Remember the true label is also from 1 to C, possibly, right? So, so this I and the Ym, they are the same kind of things. You can compare them. So there are two different cases. If I that you take here is equal to Ym, yeah, for this particular data point, given this data point, you already know what Yn is. Yeah. So if it is equal to Ym, now you take this gradient with respect to I, yeah, like that, and for En, so this is gradient with respect to Wi, just by our definition is minus log of E I. Now I can replace it by Ym, right? I should have put I there, but because I is equal to Yn in this case, I substitute Yn inside. Yeah. And this J equals to 1 to C, EW of J transpose Xn like this. Yeah? Okay. So with the softmax, it's we have a numerator that's e to something. When we take a log, this ratio, we can break down this log of the ratio as the difference of two logs. Yeah? And then when you have the first log, the log of e basically just give you the exponent, right? That's why we want to break it down first. Yeah? So still you have this nabla of Wi, and then the first term would be minus just the exponent of the numerator, yeah? Because the log of e, xn, like this. Yeah. And then I have plus here because minus, they cancel out. Yeah? So log of summation j equal to 1 to c, e wj transpose xn, right? Yeah? Okay. Now, what do we do now? In fact, this I is equal to Yn, so do I even need to write it? Anyway, so the first one, the gradient of the first term, this wi is the same as wyn. So we have seen this last time, that this simply gives you the vector of xm. Yeah? So this is minus vector of xm. And then you have the other one, which is the just gradient of the log, so 1 over. Yeah? And then after that, you have the sum, right? So j equals to 1 to c e wj transpose xm. And then what? You have to take the gradient of inside the log, yeah? Chain rule of differentiation. When you take the gradient of the sum, only one term matters. The others are constant with respect to w, yeah? Only the i's term or theyn's term matters, right? So only that one, then you take the gradient of the e to the something, you also have e to the something. Just the same thing we have done last time, right? Just multiple rounds of applying the chain rule of differentiation, yeah? So this is e wj transpose, no, not j, the I, right? Or more precisely, yn. Yeah. Only that term matters, right? And then finally, you take the term, the gradient of the linear term, because that's the last step of the differentiation by the chain rule, yeah? So we get to this end, yeah? Again, we have seen this last time, so really nothing new here, okay? Just I compressed a few steps together because this is not the first time we see this, yeah? So this is for the cases I equals ym, okay? But of course, in general, y is not equal to ym. In those cases, what is this gradient? Turns out it's different. So I'm going to just copy and paste this part, I think, because this part there's no change. Yeah. Except the yn have to change inside. No, I should not say there's no change. There is some change, yeah. This yn should be just I now. Yeah. Okay. Oh, no. What am I doing? Never mind, I'm sorry. Yeah, still yn. Yeah. Just by the definition. Just by the definition of this P here, yeah, by the hypothesis P. So you see ym. But now our I is different, wi is different from wym. That's the only difference, yeah? Yes. We are not looking for the probability of it's not equal to ym. We're just saying that we know what yn is for this data point, and we have to take the derivative for all possible i's. So there are all these different cases that we have to worry about. That's all. Yeah. Okay. So depending on what I is, yeah, if I is not equal to ym, then the derivative becomes this form. I hate this shape, blah blah. So let me write it again like that. So now the difference is that the first term's derivative becomes 0, yeah, because I is not equal to ym, yeah, and only the second term has a answer. So I can still copy this. What have I done? You know what? I'll just write it. EWI now transpose xm. Times xm, like that. Okay? So turns out depending on what I is, you get different values for this gradient. So this is only one component of that long gradient vector, right? Remember, the long gradient vector is this guy, yeah? On the top there, yeah? So we have to find all of the components. So one of the components would look like this, yeah? The rest, the C-1 components will look like that, Okay? Yes? Our what? Our labels. Doesn't matter how you encode it. You have this yn. You know that yn has to take the value 1 to c. For this particular definition, yn, we define it as that number, 1 to c, one of the numbers. How you code is a different issue. How you program this into your computer, that's a different issue, right? We don't have yn transpose. Where do we have yn transpose? No, this is a w of yn transpose. The w is the vector. Yeah. So this is the same as wi, right? wi transpose. We're just saying that yn can be equal to I, right? It's just an index. Yeah. It's the index between 1 to c. Yeah. Okay? Yeah. So this is a bit different, right? It's a bit less trivial, yeah, than the logistic regression for the binary case, yeah. So a bit more involved to compute this. Okay, but it's not hard. You still get the closed form solution for the gradient, and therefore you have the gradient to carry out your gradient descent, and you can solve this multi-class logistic regression problem. Yeah, so we're all done with multi-class extension to the logistic regression method. There's one question remained. If you think about it a bit, compared with the binary case, you see that this is the same, exactly the same as the binary case or not? What would be the binary case if we look at this? This is supposed to be a general form, right? C equal to 2 is a binary case, yeah? Okay, but even if c equal to 2, this does not look like our binary logistic regression. Or does it? Okay, is it the same or not? Yes?
I'm just curious because if c is equal to 2,
yes.
I guess it would be like the 1 over 1 plus. So you end up, I guess, ends up if you simplify, that's like the normal case.
Yeah, you can simplify it, yeah. So it turns out they should be the same, right? Because this is just a general form, there's no reason to get something totally different, okay? The question is, how do we make them the same for this case of c equal to 2, yeah? So the answer is, yeah, you try to shift things around, normalize and divide things and see whether they are the same or not, okay? So it turns out they are. So I write this here, soft max for c equal to 2. Oh, I actually say software regression. Yeah, software regression. So what is the case of p big omega of 1 given x for softmax? Well, by definition, is simply EW, the first one, with x, and then here we have only 2, so 1 transpose x, and then plus e to the W2 transpose with x, right? And as suggested, so let's just massage this into a form of that sigmoid function that we have. In the sigmoid function, we have x e to something above, and then 1 plus e to something at the bottom, right? This can be achieved easily by just dividing e to the W2 transpose x on both the numerator and denominator. Yeah? We divide e to the W2 transpose x in both the numerator and the denominator. Yeah? So when you divide that, then this becomes e W1 minus W of 2 transpose x, right? And then this one, simply you have, well, I can write the first term first, doesn't really matter. 1, this W2 transpose x plus 1, yeah, right? So that now it's the same form as the binary case. And then let's also double check, what is the other case equal to this? Yeah. Of course, it's e to the 2 transpose x. Yeah, the denominator is the same, plus e w2 transpose x like that. Easily you can see that it's 1 minus the p of big omega of 1. Yeah, because they sum to 1. Yeah? The denominator simply normalizes everything. Yeah. And that's exactly logistic regression, except that our label was plus 1 minus 1. Now you just change the 2, the label, to minus 1. The label doesn't matter, right? Whatever you call it. A dog, a bird, or whatever. Yeah? So this logistic regression with W equals to W2, that difference. Okay. We're interested in softmax regression because it is one of the common output layers of a neural network. Okay, you see this all the time in neural networks as the last output layer. So one of the most common purpose of a neural network is also for classification, right? In the output, the neural network needs to output is a bird or a cat or a dog, yeah? Different choices. Basically, you output the probability. Yeah. And it will be of the soft, most of the case, it will be of the softmax form, yeah? And our analysis about logistic regression being a maximum likelihood estimator, and also it is the same as a cross entropy measurement of goodness of distribution, still holds when you have multi-class logistic regression. Yeah? You can easily see that the same analysis will go through when you have C greater than 2. Okay? So therefore, softmax regression is still a very meaningful method of learning, and as I said, also it's a very practically useful. We use this all the time as just the output layer of a neural network. Okay. So in general, if you have simple classification problems, people just use logistic regression or softmax regression. You can solve the problem, no worries. And then when you have more complicated problems, like identifying a complex image, then what you want to use a neural network, many layers to work out things a bit more, and then you send it to the softmax regression at the end. Yeah. That's generally how it works. We'll start to talk about neural networks next time. Any questions about softmax? So there's one more topic that I want to discuss about gradient descent. Actually, I'm sorry, two more topics. One is gradient descent can also be applied for linear regression. We're going to talk about it now. And then later we'll talk about gradient descent for non-convex scenarios. And then after that, we go to neural networks. So gradient descent or stochastic gradient descent for linear, not regression, or not logistic regression, but linear regression. Okay. If you remember linear regression, we also have to design the line, yeah, or hyperplane, this W, and then the in-sample error is defined again as the average of the per sample error, yeah, and then where En per sample error is given as the difference between the true label and your estimated label, right? For regression, the estimated label is simply this weighted sum of the input, just like that, right? We have seen this, and everyone should know this very well because really pretty much in the one-dimensional case, this is what you have seen even in high school, yeah? So if you want to use logistic, gradient descent to solve this problem, then we have to find the gradient of this En. Yeah. So no big deal, right? Just take the gradient. So this gradient of the square error. Okay. And again, the formulas that we have learned before turns out still apply in this case. When you have a derivative or a square or something, you get 2 times the same, right? So which is this inside the square. And then you have to use chain rule differentiation again. So take the gradient of whatever that's inside. Yeah? And the second part is easy because it's only a linear function of W. So this is simply xn. Yeah? Okay. Again, we have seen this many, many times now. These kind of simple formulas you can just simply remember. You don't have to derive it every time. Okay. So, and of course, this is a square form. We know that this is convex. It's easy to show that this is convex, even if you are not convinced at this point. Yeah, you can take the second order derivative, yeah, and show that it is positive semi-definite, and then you know this is convex. So because it's convex, we know that when we run gradient descent, it will converge to the optimal point, yeah, the absolute optimal point. So when you run GD and SGD, as the steps goes to infinity, WT converges to the least square solution. We know the least square solution that we derived before is optimal, right? So the solution, the optimal solution, which is, remember the least square solution? It is the pseudo-inverse multiplying the output vector of y, yeah, right? Okay. So everyone okay so far? Everyone agree that that's what will happen, right? You run GD, you go there. Yeah. But then there's a natural question then, right? We already know how to calculate this optimal point. Yeah, right? Just substitute in the formula. Why do we want to bother with GD or SGD? Why do we even care? Yeah? Okay. Okay, this is one good answer, yeah? So one reason is that this calculation can be highly complex if your n is large, okay? So this one, you can work out the arithmetic. This one, the complexity turns out to be md squared plus d cubed, okay? That's the complexity. I think this is the number of multiplications, maybe, yeah. But anyway, complexity, yeah. Okay. So one reason that we prefer GD or SGD is that that one could be very high when n is large, yeah, and then also d is large as well. In that case, you're going to be in big trouble. So computational complexity. And whereas for GD, it's O of md, right? Not md squared. And we know that if you don't like the GD complexity, you can have a lower order complexity, just OD, right? For the single sample SGD, or you can do mini batch SGD, right? This is per iteration. Of course, you have to do multiple iterations, but usually the number of iterations in general is smaller than n. And you can get pretty good, pretty close optimal before you hit the nth node, the nth sample. So this is one good reason is the complexity, okay, for large problems. Anyone has read about this before? Yeah, that it's a bit more advanced. Yeah.
This is just a guess, but I remember there was a specific focus on that the data is linearly separable.
Okay.
Is that related?
This is linear regression, so no, we don't have anything about. Yes.
Just a question. So you're saying it's faster to do gradient descent than to multiply the matrices?
Yes, in general, this is if you have large N and large D, then running this will be faster than doing that calculation.
And I guess there's no guarantee that the matrices are invertible, I guess.
Okay, that's kind of a good point, except but in general, in the big data case, N is much larger than D, so it's easy to find D samples that are linearly independent. So usually this is true, so we don't worry much about that. Oh, no, we already talked about that. This is included, yeah, that's included.
To avoid overfitting and fitting the noise.
Yeah, to avoid overfitting. That's actually a more subtle point here. That's actually more important reason than the first point, okay? Very often we don't want to find the optimal solution, okay? Yeah. You say, wow, we've been talking about optimization for all this time, all these weeks, and then suddenly you tell me, you don't care about the optimal solution. Why not? Yeah. Okay. What can be wrong? What can go wrong if I just use the absolute optimal solution? Yeah, this is only for the optimal solution for the training data, right? There's no guarantee that this is a good solution for testing data. And in general, if you have noisy data, it's actually bad. You optimize it to fit the best to the noise. Okay. So in real life, we want to control the testing error as well, not just the training error. The way that we control the testing error, we set aside some data points to run validation. We're going to talk about validation in more detail later, but you can get the chance to do validation in your programming assignment anyways. It's a very simple idea, right? You just set aside some data points to double check whether your answer is good or not for those data points. Now, those data points, you don't use it for training, right? So they are like kind of like simulating the real world, yeah? They're simulating the testing. So that's what validation is, yeah? So you use this validation data set to check whether the answer is good or not, okay? But you want to have a chance to control this, right? To check whether it's good or not. That if it's good, then you can stop. If it's not good, then you keep training, yeah? But if you just do this one jump to to the optimal solution for training, you don't get the chance to validate, right? You don't have this one solution, and that's it. You don't have a choice, yeah? So it's not desirable. In fact, it's better to run GD step by step, and along the way you can check whether my current solution is likely to be good in testing. Okay? So that's the benefit of GD. So exact solution may not be, in fact, very often it's not, yeah? Desirable. In reality, of course, we only care about the testing error, right? Not the training error. We only care about E out. Yeah, so which is the testing error, not E in. E in is just a proxy for E out. Yeah, we're hoping that they're close. Yeah, but at the end, we only care about E out. And therefore, in practice, we want to run a few iterations in GD. We do validation. Again, the idea of validation should be kind of simple enough to understand, right? We don't have to formally define what validation means, right? At this point, yeah. And then we stop when the error over the validation set, validation data set is good enough. And if you do this, the following will be what you tend to observe. Okay? And this is t, the iteration, so let's go on. This is y-axis is the error. Yeah? And if you look at E in, this is convex, right? So E in, of course, keeps going down until it goes down to 0, right? No, I'm sorry, not to 0. Until some minimum point, yeah? And then it becomes flat, yeah? This is E in. Yeah? Converges to the optimal point, lowest point possible. Yeah? But E out, because of overfitting, it never looked quite going down together with E in. At some point in time, it will start to pick up. Yeah? That's the time that you are basically training too much. You are fitting to the noise. Okay? And how do you know that E out is picking up? Well, you do validation. And of course, there's an assumption, some mathematical analysis you can do to say that, well, the validation error is similar to the testing error. Okay? So, and therefore, it makes sense that you have some good estimation of the E out. So my pen is not working. Come on. I don't know what's wrong with it. Where's my backup? So around this point, you will stop. Yeah, you can as soon as you see the E out picking up, usually we just stop the training. Okay. So in this hour, we have seen multi-class, and then this other topic about why we might want to use GD even for problems where we know exactly how to find the optimal solution directly. Yeah, there are other problems where you can directly find the solution, but usually we don't do it. Okay, so these are the two topics. Any questions about anything? I might have run the multi-class a bit too fast, because in case if some of you are not very comfortable with your calculus, so I have a bit time left. So any questions about anything before we take a break? Yes. Yeah, you can think about it, see different lines in the space.
You can think of it as two-dimensional, basically, for example, right?
You could, yeah, but we don't. Usually that big omega is just one long vector.
Oh, I see. Okay.
Yeah.
And then the answer that each of those vectors give, like W1, W2, those are basically arranged between 0 and 1 relating to that label, right?
The W's are not 0 and 1. The W's are...
The output that they give. So for example,
yeah.
W1,
right, right.
If it gives, for example, 0.5, that means
okay.
there's a 50% chance that they give this label 1, right?
We don't interpret it this way anymore, because it's very hard to interpret the way that you want it to. Okay, we'll just interpret as these different lines will give you the probabilities of each point being one of those labels. Yeah. Basically, if you have a point in space, maybe do I have no? That's an interesting question, since we have a few minutes. If you have multiple lines like that, and you have a point in space, you say, well, I have to decide whether this point belongs to one of the three labels. Okay, which one should I assign it? Which one is the most likely label for this point? Okay, so it turns out that what this thing does, the softmax, is to basically, roughly speaking, just measure the distance of this point to these three lines. Okay, turns out that the furthest away line will be the most likely label for this one. So we have three labels, so 1, 2, 3. So this point would most likely be labeled as a 3.
And the addition of those probabilities will be 1.
Yeah. Those probably have to be equal to 1. Okay. The longer, the further away from the line, the higher probability you will assign for that label. That's how we interpret this softmax. You have a question before? The weights for AI? Oh, you mean for machine learning model? For this W, depending on the problem, for the say the lossless regression, finding the W. Actually, I don't know. It is a convex problem. Actually, convex problems are known to be polynomial time. Actually, it's not. Yeah, it's a polynomial time problem. So it depends on the loss function itself. For linear regression, lossless regression, no, it's a convex. But when you have non-convex, yes, in general, it will be NP-hard. Yeah. Good. Okay, so we'll take a break. We'll come back at 2 o'clock, 3 o'clock. Yeah. 3? No. Oh, no, sorry, yeah, no. Okay. 2:10, 2:10, we come back. Yeah. Okay. If I can fix my pen.
Are the notes you post on Quirk identical to these?
We have 2 sections. Usually I pick the second time that I teach because it's more, organized. It tends to be, yeah.
I actually got a question for this part.
Yeah.
So when we were doing this part, isn't like you expand it in this way?
Yes, we do.
But for log, like, where like the rest log
No,
E?
log of this E is simply this, right? Log
Why?
is E, they are inverse. They are inverse of each other. Log of e to the x is always equal to x. That's the definition of log, in fact.
Log of e to x
You
is
see
x?
it? Yeah, that's the definition of log.
Isn't like ln?
Oh, this log is natural log. Whenever you don't specify the base, it's by definition the natural log.
Natural log is 10 or e?
No, it's E.
Oh, okay.
for this thing, for multi-class logistic
Yes.
regression,
Yeah.
I was looking at some of those notes, and
Mhm.
you interpreted it as having a bunch of lines and seeing where the dot is closest to.
Yeah.
Right?
Yeah.
But wouldn't it be a better interpretation if we consider each weighting to
Mhm.
be like a direction vector, right?
Okay.
And direction is a line of like that classification, right? And you know how when you take a weighting times, when you do this, right, that's technically a projection of this onto that line, right? Right, well, you're getting the coefficient, like the overlap coefficient, right? Yeah, so I'm thinking of it as if we have like some dimension, right? Let's just take dimension 2
no, you have to be careful now. This, yeah, there's a projection here when you look at the vector W,
Yeah.
but then the line is not the vector W, right? Vector W is the coefficient for the line. W is orthogonal to the line.
Yeah, but if we don't take it as, if we don't treat it as a line, but if we treat it as a vector, right?
Okay. You mean W? You treat W as a vector, or do you want to treat the line as a vector?
Well, W is the line, right?
No, W is the direction that's orthogonal to the line. That's what I was trying to say.
Right.
W represents the line.
Right, yes.
It's
yes,
orthogonal
right.
to it, yeah.
Yes.
So when you take a projection of X onto W, it's the same as saying that I want to measure the distance of this point to the line.
Right, actually, yeah.
Yeah. So it's the same thing.
Yeah, because I was trying to think of it in terms of like, you know how if they are more or less pointing in the same direction, then their values would be, bigger. And if they're pointing in the orthogonal direction,
Yeah.
you kind of know that they're not
Yeah.
correlated at all.
You can roughly think about it that way, but also that the value matters, right?
Right, but
Yeah.
I guess the projection is just the distance. Yeah.
All right, okay, let's restart. So one more topic about GD. It's a big, we've spent quite a few lectures on GD because it's so important in modern machine learning. Very often we don't really have a good method to optimize our function. Then we just have to do gradient descent numerically, step by step, hope that it converges to something good, something that has a low value. So we have seen so far for convex functions, we always get to the optimal point. And even if you don't want to get to the optimal point, it's also good that if you need to, you can always get as close to as you want, or as whenever you want to stop, you can get there. So it's good to know that you can get to the optimal point, even though, as we discussed last time, in general, we don't want to get all the way to the optimal point. So logistic regression, linear regression we have seen so far. They are convex, yeah, the E in of W. And you know, one-dimensional convex curve looks like this, and you have high-dimensional two-dimensional inputs. You can imagine a bowl, but then when you have, you know, three-dimensional X, then it's we cannot visualize anymore, right? Anything higher than 3 dimensions is very hard for our human brain to visualize. Apparently, our human brain, that means our brain is trained in our universe, right? So to escape from tigers or hunting deers, you know, our brain is not trained to think about high-dimensional space, time, space, continuum, what not, yeah? So you know, that's our limitation. So in this case, when you have convex, then we have global minimum. And that's also the case when this gradient is equal to 0. Yeah? So the question then is, well, what about non-convex functions? Because we have to deal with them all the time in machine learning. So, well, a non-convex function, let's draw a one-dimensional case. Make it more vertical. Let's say it's x, yeah? D equals to 1, so f of x. It might look something like this. That, yeah? This will be non-convex. And you notice that we don't have a single point like that where the E in gradient equals to 0 anymore, right? We have, in this example, we have 3 different points where the gradient or the slope will be 0, yeah? The derivative is 0, okay? So we have, if you look at the gradient of fx equals 0, then you see, in this case, 1 of them, 2 of them, 3 of them. The first one on the left, yeah, that turns out to be our, you know, well-trained brain can see immediately that's the global minimum, yeah? That is the real minimum. Because our eye can see the whole function, yeah? And then on the right side, that one is also a kind of a minimum, yeah? It's called a local minimum, yeah? In the sense that at this point, yeah, it is small, it's a lower value than all of the points around it, yeah? But then it is not the lowest point in the function, yeah? But it is lower than all of the surrounding points. In that case, we call it the local minimum. Yeah? We can precisely define that, but you know, we don't do it here because it's not important for this course. The middle one also the gradient equal to 0, but that one is actually pretty high, right? It is the highest point in this neighborhood, yeah? So this one is actually a maximum, yeah? It is a global it's a local minimum maximum because there are other points that's higher than it, yeah, further away. So this is a local maximum. And the maximums and the minimum together, they are called the extremum, extrema of a function. Yeah. So one problem with non-convex function is that we often have multiple extrema. Okay. And where the gradient is 0. Okay. So if we say, well, let me try to find the W for our loss so that the gradient with respect to W is 0, you never know what you get, right? You may get a global minimum if you're lucky. You may get a local minimum, but in fact, you can also get a maximum as well. Yeah, you can get some of those worst cases as well. Yeah. So just knowing that the gradient is 0 is not enough in that case. Okay, so it's highly complex. And this is complicated enough. More than this, you can also have the so-called saddle points. Okay, one of those most dreaded locations in optimization. Okay? Saddle points. A saddle point is a point where the gradient is equal to 0, but it is neither a maximum nor a minimum. Okay? This is equal to 0. The bar here for 0 is a vector. But x is neither minimum, whether it's local or global doesn't matter. It's just not a maximum. Okay. When can this happen? Well, those of you who have seen saddle points before, you know this figure very well. Yeah, in one-dimensional space, one common example is fx equals to x cubed. Yeah, and if you plot this guy, what does it look like? X cubed looks like this. Okay, at the point 0, the derivative is actually 0. Yeah, you can easily check that. F prime evaluated at 0 is 3 times x squared, right? Yeah, 3 times x squared, you substitute x in there, you got 0. Okay? But this point is neither a local minimum nor a local maximum, right? But still, it has gradient equal to 0. Okay? There's a problem. Why do we hate these kind of points? If I do gradient descent, right?
There's not really information on whether we're actually, because it's not really like neither minimum nor maximum.
That applies to all of these extremums and saddle points. Yeah, but for saddle points, you know the saddle points are in the middle, right? So you're not even close to any kind of extreme points. Yet still, when you do the gradient descent, you go down, go to here, the gradient is 0. How does gradient descent work? Remember our learning rate multiplying the gradient, right? But here the gradient is 0. You're not moving anymore once you get to this point, right? Make sense? In gradient descent, your step size multiplying the gradient. But over here, the gradient is 0. So you're not updating your W anymore because the update part is 0. You just get stuck here, yeah? But of course, in reality, you never quite hit exactly 0, right? You're off by a little bit. But still, the gradient is so small that your progress is very, very slow, right? Your change in W is very, very small, yeah? Because the gradient is small, yeah? So you get stuck here for a long time. And many iterations, right? And of course, in reality, we have to set the maximum number of iterations to prevent the infinite loop in our code, right? So usually, if you hit here, you iterate many times, you hit that maximum number of iterations, then you're done. Your program just stops, yeah? Even though you don't exactly hit 0, right? Okay, so that's the idea. That's why we hate these kind of points. Yeah. So we're very slow progress. Yeah, in the extreme case, such progress is exactly 0. Yeah, near the saddle point. Yeah. And so that you loop so many times in your code that the preset number of iterations will expire. Runs out. Okay. Now, this is one-dimensional space. It's already bad enough. Let's look at n-dimensional space. The saddle points, this is, well, I should not underline it because underline is the saddle point. Okay, we're still talking about saddle points. Okay. In n-dimensional space, what kind of saddle points? Well, one kind of saddle point is that we have a one-dimensional saddle point at in any direction. yeah, then we define that as a saddle point for our problem. Like that. Yeah. But in high-dimensional space, there's another kind of saddle point, which is that it is a maximum in some direction, and then it is a minimum in another direction. Okay. So you still have the gradient equal to 0, right? But then it is kind of this weird thing, right? It is not a good point to use. Yeah. So it is a minimum in some direction. And it doesn't matter if it's a global or local one. Equally bad. And maximum in some other direction. I'll draw a picture very soon. Yeah, some other direction. And in fact, that gives the name saddle point. Yeah. For example, if I have a function that looks like this, and this side is like that, here, like this. Yeah. Basically, draw a saddle shape, right? Yeah. So if you look at this point here, let's say this point here, and if you look at this line, in the what happened? Okay, here we go. Yeah, in the blue line, for the blue curve, it is the maximum point, right? It is a maximum. But then for this direction, this lengthwise direction, it is the minimum. Yeah? So that's how you draw a saddle, in fact, right? Okay? So I would say there are in this direction, it is a minimum, but in this direction, it is a maximum. Yeah? Okay. Make sense? Does it? Yeah? Okay. So that point is neither a maximum nor a minimum, but then still the gradient is 0. Yeah? So it is still what we call a saddle point. Number 3 is a combination of 1 and 2, obviously, right? In some other dimensions, you have those kind of cubic, whatever shape, yeah? So really messy, right? So both 1 and 2. Okay? Right, so n-dimensional space, these weird things can happen, right? Yeah? And an important point in machine learning is that we always have to deal with very high dimensional space, right? Because our model, the number of parameters in our model is our dimension. Okay, we tend to have many, many dimensions, high dimensional space. And this situation happens very often, yeah? Because you have so many dimensions for this to happen, so many different directions to go, that for this kind of things can happen. So you have a lot of saddle points in high dimensional functions. Yeah, lots and lots of saddle points. Very hard to deal with. Okay. So highly likely to have, because there's so many different cases that can create a saddle point in high dimensional space. And unfortunately, we cannot avoid high dimensional spaces in machine learning. Yeah. So again, at the saddle point, by definition, the gradient is 0, right? That's the definition of a saddle point. Well, gradient is 0, and then it's not a maximum minimum. When the gradient is 0, we get into trouble with our gradient descent methods. But then gradient descent method is really one of our only ways to solve this kind of problem. So where we don't have a closed form for optimization. Yeah. So we have to find a way to deal with it. Okay. What do we do? So there are some simple things you can do. Yeah. First of all, you do the stopping condition. You want to reduce the chances of stopping at a saddle point. Yeah. You try to reduce it's not very effective, but at least something that we always do anyways in our optimization. Yeah. We don't want to get stuck at saddle point. And one is that we don't wait for this gradient to be exactly equal to 0. Yeah, we just stop when it's close or close enough. Or we check the value itself directly. If we have a way to understand what it means for the loss to be small, then we just stop when this loss is small. Okay, but this is take it with a bit of a grain of salt. Okay, do you really know for your particular problem when is small? What's small is small enough? Yeah. Another thing is, of course, your number of iterations. You just when it's very large, then you stop. You just say, okay, probably that's enough for my optimization. Yeah. So these are kind of the simple things that we do. Yeah. We do all the time, anyways. When you code your program, you should always code these things in somehow. Yeah. But the more effective method is to improve SGD or improve gradient descent with what's called the momentum. Okay? What does that mean? Momentum. So we do say SGD or GD, GD / SGD with momentum. You know what? Since I'm going to just do, I will only write SGD. So let me just write SGD. But the GD version is the same. Also, the mini batch one, you can also easily extend it. Yeah. And this idea was not new at all. People have been thinking about this kind of optimization problems for a long time, right? It's first published by Polya in 1964. Okay. So the goal of this is to accelerate the convergence of SGD, yeah, and try to avoid getting stuck at a saddle point. Yeah. So the basic SGD, just as for comparison, we first define this GT, right? Is the gradient at this point, and then you update W is WT minus GT. It's a bar under G. It's a vector. So the idea that we don't want to get stuck at the place where this gradient is small. Yeah. So you want to give your optimization a push to get through this point that's flat. Yeah. So what is that push? Well, it's called momentum. It takes the analogy from physics. But when you have a ball going down the hill, there's a certain movement, some certain velocity. Yeah. Mass times the velocity is a momentum. Yeah. Yeah. If you think about the mass, it's normalized to 1. Yeah. So essentially, momentum is equal to the speed of movement. Okay. So you want to account for the current speed of your optimization in the certain direction as well, beyond this simply looking at the gradient. Okay. So the next step, you consider the current gradient, also consider your momentum, your movement history, yeah, the historical speed of the optimization. Yes. The what? Oh, it's a learning rate. Yes, or the step size for the updates. Yeah. So SGD plus momentum, that's exactly the idea, taking from a little bit from physics. So again, you have the gradient, GT, Now you define this new variable, this new vector called vt, which is the epsilon t times gt, what you would have used as update. But now you also take a discounted version of your previous velocity, vt minus 1. Okay? Minus 1. Yeah? And then your new location would be this old location plus the velocity. Yeah? You think about the W as the location of a ball, yeah? V is the velocity, yeah? And that G part would be kind of the acceleration. Yeah? Yes?
Just so from you here, is that also a linear that we set for discount?
Yeah. The mu is between 0 and 1. Yeah, I need to write it down. So usually, it's a discounted factor of the historical velocity. Yeah, and one common example would be mu equals to 0.9. Yeah, very commonly used. Other common numbers are 0.5, 0.99. Okay, depending on how much you want to account for the historical velocity. Yeah, it's another one of those hyperparameters that you should tune. Oh, you mean vary the mu? Yeah, but people usually don't bother to do it. Yeah, for the momentum, people just use a constant. And there isn't a lot of theory here. It just kind of hand waving, choose whatever constant that feels right. You know?
What would we do for VA1, the first one?
Oh, you just set to your momentum is at the beginning is 0, right? Let's say, yeah. So just epsilon 1 times g1. Yeah. So again, this is a accumulation of your previous movements, right? Since in every time step you just keep accumulating this, but with a discounted fashion, so that you don't go to infinity, of course. Yeah. Accumulation of previous movements. Yeah. Exactly the idea of a momentum in physics. Yeah. So how does it work? Well, it helps in 2 ways. First of all, momentum helps you to escape a flat region, as we expect. Helps SGD escape flat regions. One example is something that saddle pointer looks like this. Let's say it's a flat here, and then it goes down, like that. So around this point, which is a saddle point, clearly, yeah. At this point, GT is 0, right? But since you're going down this hill, right, you have some previous direction. When you're optimizing, you know that you're going to the right, yeah? So if you just remember your past history, you know that the velocity is going this way, okay? Therefore, when you substitute this into the update, you will not get stuck here. You just keep pushing to that side, yeah? In fact, this one is so effective that it can not only help you get around saddle points, it can also allow you to get around the shallow local minimums, or shallow local minima, to go out of a shallow dip. So another example is that you might have a little dip here, not too heavy. Yeah, if too heavy, then maybe it does not help. Yeah, like that. So if you're here, and this is a let's say shallow local minimum. Yeah. You don't want to be stuck there, right? Because you actually have a much better solution down there. Yeah. So again, but here is the gradient is 0, right? Gradient descent would, if your step size there is small enough, the gradient descent would just get stuck there, and that's the final answer you get, right? Yeah. But if you use momentum, again, because this ball has been, this optimization has been coming downhill, and the velocity still has this direction to go, yeah? So you just push yourself go over the hump, and then now you have a chance to get to a better minimum point. Okay. And both of these, we use the analogy of a ball running downhill, right? So exactly, that's the Pouliot momentum is also called the heavy ball momentum. Yeah? A very technical term. Heavy ball momentum. Okay. So this is a kind of a somewhat obvious benefit of having momentum. Yeah. There's a second, more subtle benefit that even when you have a just completely convex function, so no issue with saddle points. Yeah. No issue with local minimum, local maximums, and so on. Using momentum can still help you speed up the convergence of SGD. Okay. So this point is a bit harder to see. Momentum can lead to faster convergence even for convex functions. Okay. So to see this, we have to go to a high dimensional space, let's say 2-dimensional space. So this function is going to be f of x1, x2, yeah? So 2-dimensional space. But I'm already drawing these 2-dimensional space here. So to draw the function, I have to use contour lines, yeah? I'm going to use contour lines for the function. I will draw it. First, I will draw the contour line will be a bit unusual, of course. I have two directions. U2, and then the contour lines are along the like this. Okay. So it's a kind of a squashed, longish cup. Yeah. Can everyone see the contour lines? Imagine what the 3D shape is. Yeah, it's kind of a cup, but then it's a elongated, squashed in one direction. Yeah, the other side is long, one side is short, yeah? Narrow. Okay, kind of a think about this. It's a long canyon. Okay, it's hard for me to draw a very long thing, but imagine in reality you could have a very long canyon. Yeah, this thing is very long, this thing is narrow. Okay. Now the gradient is always perpendicular to the contour lines, right? Because the gradient is the steepest ascent direction. So it's perpendicular to the contour lines by definition. Yeah? So if you look at the gradient and then do gradient descent, let's say we are starting from somewhere, I don't know, let's say here, yeah? It's perpendicular to the contour line, so you get there, yeah, let's say. And then perpendicular to contour line, you jump here, yeah? And then jump there, yeah, like that. Because it's so narrow, right? Yeah? So perpendicular to the contour line means that you are just ping-ponging back and forth, right? Potentially. Even if you don't ping-pong, you just go in this direction, step, right, in this kind of direction anyways, yeah? Even if your step size is small, yeah? But here I'm just assuming the step size is bigger, so just to make a more extreme point, yeah? So still the point is that your gradient descent will not be going really at the right direction, because say clearly this point is the optimal point, yeah? Okay? But your gradients are not really pointing at that optimal point, yeah? Because of this special shape of the canyon. I should say, so one way to see this is that the gradient descent will strongly favor the U2 direction, yeah, the narrower direction. Here is the U2 direction. Yeah. And another way to look at this in a most 3D shape, I'm going to slice this thing, slice the canyon open along the U2 direction. Okay, I take a section along the U2 direction. Yeah. Let's slice fx along the U2 direction. So this canyon will look like something like this, right? A deep canyon with a very narrow opening, yeah, but very long. Okay, and we're trying to get to the bottom, right? But because of this, the GD will point you to, okay, one step, you would go here, yeah, and well, let's say it's narrow enough that it goes here in this extreme case, and then you get bounced to the other side and bounce like this, yeah. Okay, so this clearly there's a ping-ponging there, yeah. Okay, and it takes a long time to get to the optimal point. Okay. How do you think momentum will help in this case? Why does momentum help?
The first jump goes as normal, but then when the second jump tries to go in the opposite direction, the first jump's momentum like pulls it backwards, so it kind of rolls down.
Okay, yeah, that's kind of one way to think about it. Is there a bit more direct way to describe this?
I guess it just forces the jump to move some direction, so it just
Okay. Okay, but how does it momentum force it to do it? Yeah.
Kind of average. It gets the average.
Average, yeah, yeah. You remember the historical speed, right? So you look at the average velocity over time, historically. Even though it bounces back and forth, the average speed is still one direction, going that way, right? Yeah? So therefore, the momentum helps push the optimization to go that direction. I mean, I should say this direction, yeah? It's going this direction, right? On average, still, yeah? So you have learned that you should be going in that direction, yeah? And that's your momentum, okay? So, but the overall trend, yeah, basically our momentum. Which is the red one, yeah, going from in this direction, yeah. Okay. It's moving along the U1 direction. Yeah. So when you use SGD plus momentum, it certainly helps you to say you should do it, okay? Because you want to go that direction. Yeah, that's the direction you want to go towards the optimum point at the bottom of the canyon. Okay, is this clear? Yeah. So that's the idea, how momentum can help, even for convex functions. And again, because we deal with high-dimensional space, in fact, very often, even for convex functions, you have, in some directions, it looks like that, yeah? And momentum really makes it much better. Have you all heard of the Adam optimizer in Python? The Adam optimizer. Oh yeah, okay. Well, we'll talk about it later. But you know, when you use Adam, the M stands for momentum. So you'll see it later. Then, yeah. So this is the heavy ball momentum by Poliak. This one, there's no performance guarantee, even though numerically we know that it works very well. Okay, no one has been able to prove there's any improvement theoretically. Until 1983, someone called Nesterov modified this, improved this a little bit. For that version of the momentum method, the Nesterov momentum method, there is a provable performance benefit. Okay, so that is an important development in machine learning or in optimization in general. So Nesterov momentum looks like this. The one of VT, the way the VT is defined, remember the VT is the velocity, right? Previously, you look at the velocity, how we defined it. Looks like this, yeah, on top there. That's the velocity. And the gradient is the current location, the gradient, yeah, at the current location gradient. Nesterov said, no, actually you should do you should look for an intermediate location for the gradient instead of this WT. Okay? And that turns out mathematically can be proven to improve things. So instead of taking g of t, you take the gradient at not at WT, but plus this. Remember what is mu Vt minus 1? That's your previous velocity, right? Some kind of historical version of the previous velocity. Yeah. So you update your location first with the previous velocity, and then take the gradient at that point, at a new point. Yeah. And then you, just as before, you add this previous velocity, Vt. Sorry, Vt. Okay. Yeah. So this is an intermediate point. Yeah. Okay. Everyone see the difference between this and the previous one? Yeah. Okay. Just go half a step forward first, calculate gradient, and then you go the full step. Yeah. And then yeah, the rest is the same. Wt is simply Wt plus Vt. Just like that. Okay. And the benefit of this one is that it's provable, that it improve performance. But even though the heavy ball one, there's no proof, numerically we still observe that it improves things a lot. Yeah? But this one is provable. Convergence. Even for convex functions. How do we measure the convergence of optimization? Well, we want to measure how far away you are from the optimal point, right? Optimal point is W star, and then our current point is WT. So we just measure at the T step, how far away are we, yeah? So basically the distance, you measure the distance between, let's say, yeah, WT and W star, the optimal point. Yeah. And usually this distance will be measured by the Euclidean distance. Then it will be the 2 norm between these 2 points. Yeah. Turns out that for regular GD, the distance between these two is a big O 1 over T. Yeah. Of course, you expect this thing to be decreasing over time, right? As T advances, you get closer and closer to the optimal point. How fast do you get close? Well, that's speed, yeah? The distance shrinks inversely proportional to T, okay? That's for regular GD, full GD. Okay? But when you have Nesterov momentum, this one gets improved to 1 over T squared. Which one is faster? 1 over T squared, this is distance, right? This distance, you're getting closer, yeah? 1 over T squared is smaller than 1 over T. Yeah? So you're getting closer to the optimal point for the same T value, right? Yeah, T is greater than 1, yeah, 1, 2, 3 to 1,000 or whatever, yeah? So therefore with this one, it's actually much faster convergence to the optimum point, right, than this one. Yeah. Okay. And the proof, again, we don't have to worry about it. It has been proven and have been checked by other mathematicians. Not the kind of problem that we need to worry about. We just need to know that there is this nice result that we can use. Yeah. Maybe there's one question about, well, this is full GD, right? What about SGD? Interestingly, SGD, I don't want to write down number because you don't have to know for this course. The convergence speed, in general, for general convex functions, is only 1 over square root of t. Okay? And then for strongly convex functions, that are basically very curvy functions, it's 1 over t. Yeah, but in general, it's 1 over square root of t for SGD. But then for SGD with momentum is still the same. For the scaling, still 1 over square root of t. So therefore, turns out the momentum, at least in theory, nobody has been able to prove that it improves stochastic gradient descent. Okay, at least for now. So far, no one has been able to prove rigorously that it improves performance. We only observe numerically that even if you use SGD, having momentum helps a lot. We just don't have a proof. Okay? But for regular gradient, it's very clear. Yeah, huge benefit. Any questions? We are going very fast today. Yeah? So am I going too fast today, or are we all doing okay? Yeah. Oh, well, I'm sure there are weird edge cases that this can perform terribly, badly, but in general it is better. Yeah. Also, even this is big O, right? You can imagine there are some coefficients that are very bad. We never know. Yeah. We doing okay. I'm not going too fast. Yeah. So just want to finish this before we move on to neural network. Yeah. So next time. Okay. So I'll see you next week.